All right, let's talk about building software. If there's one single truth, it's that things are always going to change. You're constantly juggling new feature requests, changing requirements, and weird bugs, all while just trying to keep your code from turning into a giant knot.
I mean, this is the classic problem, right? You get a request that sounds simple enough, but you make one little change over here, and suddenly everything over there just breaks. It's chaos. So how do you actually build software that can grow and evolve without collapsing on itself? To figure that out, let's follow a story.
And believe it or not, the answer starts to take shape in a simple little duck simulation game, and with a programmer named Joe, who's about to learn a very powerful lesson.
So, this is Joe, and his whole world right now is a game called SimUDuck. It's full of all kinds of ducks. And in the beginning, life is good. The requirements are simple. The game has different types of ducks, and they all need to be able to swim and quack. Sounds easy enough.
So Joe does what any of us would probably do. He reaches for inheritance. He makes a main duck class, a superclass, that handles all the stuff ducks have in common. You know, the quack method and swim methods. Then the specific ducks, like the mallard duck or the redhead duck, just inherit from it. A mallard is a duck. It's a clean design, there's no duplicate code, and everything just works. For a little while, anyway.
Because, as you know, things in software never stay simple for long. A new feature request comes down the pipeline, and it's about to completely wreck Joe's nice, tidy little world. The mandate comes from on high. It's a big one. To beat the competition, all the ducks in the game now need to fly. The pressure's on, and Joe has to make it happen. Fast. So what's Joe's first instinct? The path of least resistance. He thinks, hey, every duck inherits from the main duck class, right? I'll just add a fly method right there. One change and boom. Every duck in the entire game should now be able to fly. It's logical, it's efficient. What could possibly go wrong? And of course, you guessed it, it's a total disaster. At the big demo for the shareholders, they're watching in horror as rubber ducks start flying across the screen, squeaking and flapping. Joe's simple fix has created a really weird bug, and he's got a flying, squeaking mess on his hands. Okay, so the quick and dirty fix was, well, a disaster. Joe realizes that just patching the problem, overriding the fly method for the rubber ducks, isn't a real solution. That's just playing whack-a-mole. Every time a new non-flying duck gets added, he'd have to remember to do it again. It's just too fragile. He's got to find a better way. His next idea seems a little smarter. An interface. He thinks, okay, I'll make a flyable interface, and only the real ducks will implement it. That seems flexible. But then reality hits, and it hits hard. An interface is just a contract. It doesn't actually provide any of the code. That means he'd have to copy and paste the exact same flying code into every single duck subclass that's supposed to fly. If he has 48 types of flying ducks, that's 48 copies of the same logic. It's an absolute maintenance nightmare. And at this point, Joe has a kind of revelation. He realizes he's been looking at the problem all wrong. He's been trying to fight change. The real solution isn't some clever coding trick. It's a fundamental shift in thinking. It's about designing for change from the very start. And to do that, you have to follow a few rules. The first big principle is this: encapsulate what varies. You have to find the parts of your application that are in constant flux and separate them. Pull them out from the parts that stay the same. In the duck game, what's always changing? The flying behavior, the quacking behavior. That's the stuff we need to isolate. Second rule, program to an interface, not an implementation. Now this might sound a little academic, but all it really means is that our main duck class shouldn't care how a duck flies. It shouldn't be hard-coded to a fly with wings class. It just needs to know that it has some kind of generic fly behavior it can talk to. This completely decouples the duck from the specific way it flies, and that's huge. And the third, and maybe the most important principle of all, favor composition over inheritance. This is the real game changer. Instead of a mallard duck being a type of flyer through inheritance, it now has a flying behavior. We're giving the duck a separate behavior object to delegate to. It's like plugging in a module. And this changes everything. So with these three principles in our back pocket, let's see how Joe finally architects a solution that's not just elegant,
but flexible enough to handle whatever the business throws at him next. So here's the new world. The duck class itself has no idea how to fly. None. Instead, it just holds on to a fly behavior object. When you call perform fly on a duck, the duck doesn't do the work. It just turns to its little helper object and says, hey, you handle this. And what's so cool is that we can now have a whole family of behaviors. Fly with wings, fly no way, even something crazy like fly rocket powered. And we can just plug them into any duck we want.
Now this new design is already way cleaner, way more flexible. But the real magic, the thing that makes this pattern so incredibly powerful, is that because the behavior is just a separate object, we can change it on the fly, literally while the program is running.
Just check this out. It's the aha moment. We start with a model duck. By default, it's set up so it can't fly. We call perform fly, and sure enough, it says I can't fly. But then, here's the magic. With a single line of code we call set fly behavior, and we swap in a brand new rocket-powered behavior. And the next time we call the exact same perform fly method on that exact same duck, boom, I'm flying with a rocket. We just gave a duck a jetpack at runtime without touching a single line of the model duck class's code. That is incredible.
So let's zoom out from the duck pond for a minute. What we just saw Joe discover isn't just some fix for his game. It's a genuine superpower that you can use as a developer. It's a reusable solution to a really common problem.
And what we've just built, it has a name. It's called the strategy pattern. The textbook definition really nails it. You define a family of algorithms, like our flying behaviors, you encapsulate each one, and you make them completely interchangeable. The key idea here is that the strategy, like how to fly, can change completely independently from the client, the duck, that uses it.
So what's the bottom line? What does this really get you? Well, first, it completely decouples your algorithms from the classes that use them. The who is separate from the how. Second, you get this amazing ability to change algorithms at runtime. Third, you get to throw out all that ugly nested if-else logic and replace it with clean, swappable objects. And the end result of all that? Your code is just way more flexible, way more reusable, and a whole lot easier to maintain.
And that really brings us to the final and most important question, the one for you. Think about the code you write every day. Where do you have behaviors that change? Maybe it's different ways of calculating a price, or different formats for exporting data, or different sets of validation rules. Every one of those is a family of algorithms just waiting to become a strategy. So the question is, how can you use this pattern to make your own code more powerful?